All right, welcome. Today, we're going to unbox the concept that's literally all around you, whether you realize it or not: surface area. So let's dive in and see how this one idea shapes our world, from wrapping gifts to designing pretty much everything.
You know the feeling, right? We've all been there. You're trying to wrap a present, you make the cut, and it's just a little too short to cover that last corner. Well, that frustrating little moment, that's actually a surface area problem in the wild.
And that's really the simplest way to think about what surface area is. It's the total area you'd get if you could measure every single one of the outside faces of a 3D object. So, in other words, it's the perfect amount of wrapping paper you need to cover something with zero gaps and zero overlap. To really wrap our heads around this, we're going to do something kind of cool. We're going to visually unbox these shapes, take them from solid 3D forms, and flatten them right out to see what they're actually made of. So, take a look at this. On the left, you've got your standard box, a cuboid. But to figure out its surface area, just imagine we could slice it open and unfold it perfectly flat, like you see on the right. That flat pattern is called a net, and it's awesome because it shows us every single face that we need to measure. And with a perfect cube, it gets even easier. When you unfold it, what do you get? 6 totally identical squares. So, figuring out the total surface area is as simple as finding the area of just one of those squares and then multiplying it by 6. See? Pretty straightforward. Okay, now that we've got the whole unfolding idea down, it's time to build our toolkit. Let's get these core formulas locked in for the most common shapes you're going to run into. First up, the classic rectangular box, or cuboid. It's all about 3 key measurements, right? Its length, its width, and its height. Now, the formula might look a little intense at first, but it's really just doing what we did with the net, but with math. It finds the area of the front, adds it to the area of the top, and adds that to the area of the side. Then it just multiplies that whole thing by 2, because, every face has an identical twin on the opposite side. Next tool for our kit, the cylinder. Think of a can of soup. It's got 2 perfectly flat circles on the top and bottom, and then that one big curved side that connects them. And the formula totally reflects that shape. This first part, the 2 pi r squared, well, that's just the area of your 2 circular ends combined. And the second part, 2 pi rh, that's the area of the curved part. If you were to peel off the label and lay it flat, it would be a perfect rectangle. And of course, we've got the sphere. It's such a unique shape. No flat faces, no edges, just one continuous, perfectly curved surface. And its formula is just as elegant. 4 times pi times the radius squared. That's it. That powerful little recipe gives you the entire area of the sphere's skin. It's a classic for a reason. Okay, basics are down, we've got our tools. Now, let's get to the really fun part, taking what we know and applying it to some trickier, more complex shapes, the kind you actually see out in the real world. So check this out. It's a super common problem. We've got a composite shape here, a cone sitting on top of a cylinder. The friend on the left has an idea. Just find the total surface area of the cone, the total surface area of the cylinder, and add them together. Simple. But our friend looks a little skeptical. What do you think? Is she right? Yeah, not quite. And here's the absolute key. When you glue 2 shapes together, the parts that touch are no longer on the outside, they become internal. So you can't include the bottom of the cone or the top of the cylinder in your final calculation. They're hidden now. They're not part of the surface anymore. Okay, on to the next puzzle. A hollow shape, like a pipe. This time, our first friend figures you calculate the area of the outside, then the area of the inside, and just subtract the inside from the outside. But her friend's shaking her head again, saying you have to think about all the surfaces. Who are you siding with this time? The second friend totally nails it again. See, when you make something hollow, you're not actually removing surface area, you're creating a whole new surface on the inside. So you've got to calculate the outside area, then add the brand new inside area, and of course, don't forget to add the area of those 2 little flat rings at the top and bottom. So who cares about all this, right? Why does it matter? Well, let's bring this whole conversation back down to earth with a fantastic real-world problem that shows exactly why big companies care a lot about surface area. So, a coffee company is testing 3 different box designs. Now, look closely at this table with me. The volume column, notice anything? They're all the same. Each box holds exactly 1,500 cubic centimeters of coffee. But now, slide your eyes over to that last column, surface area. Whoa. Design C, the one that's shaped most like a cube, uses way less cardboard than the other 2. The whole point here is to be efficient. The company wants to pick the design that costs the least amount of money to make. And this just perfectly shows how math and money are connected.
And here's the big takeaway. It's really simple. Less surface area means you use less material, and less material means you spend less money and you create less waste. By picking Design C, that company saves cash and is a little bit better for the environment, all because they understood some basic geometry.
Which brings us to one last thing to chew on. If you want to hold a specific amount of something, say a liter of water, what's the most efficient shape you could use? If you had a perfect sphere and a perfect cube, and they both held that exact same amount, which one do you think would have less skin? Which one has the smaller surface area? It's a really cool question, and if you look around, you'll see nature has already answered it for us.